Perfect. Hey everybody, welcome to our last lecture of the Python DeCal. It's unfortunate that it's on Zoom, but we're here to support the strike and everything, and we don't want to make you all come onto campus if you don't have to. So we appreciate everybody who's here. We are recording it in case anybody couldn't make it, but this is a really important lecture. It's the last one. I think it's a really fun one. And we'll have some closing remarks on the course, as well as give you some information regarding your final projects that are going to be due soon. So thank you everybody for coming, and let's go ahead and get started. Some quick announcements. The final project presentations start in 2 weeks. 2 weeks. That's going to be starting on Wednesday, November 30th. So that's the week after Thanksgiving break. You're going to have to do a presentation. Your entire group is going to have to do a presentation together in person. Like in Campbell Hall. It'll be 10 minutes of presentation per group, 7-minute presentation, 3-minute questions at the end. So prepare for a Q&A or like a Q&A on your work. Everybody has to speak at least once. Brief background, process, and final results is typically the structure you're going to want to structure your presentations in. There'll be more information on this in an assignment. We're going to post it either today or soon, or in the next few hours. I think we're going to post that for everybody if it hasn't already been posted. And then I just want to note, everybody, we take this very seriously. This is kind of what you need to pass the class, more so than the homeworks. If you don't present your work in a final project form, you don't show up for your group, it's very likely you will fail the class. We don't like doing that, but we think this is arguably the most important part of the course. So please show up for it, for your group, and as well as show up for out of respect for everybody else. We're also going to take a group picture on that day, and also more on that in a second. So we take this very seriously, please.
James.
Ooh, yeah. Sorry, yeah. Yeah.
When the groups present, it's random, right?
Yes. Yeah, that's a good point. So on Wednesday, prepare to present. Everybody should be prepared to present, because everything's going to be due by the start of Wednesday's lecture, and we will pick at random. So people will just be prepared to present on Wednesday. So everybody should show up on Wednesday. And then out of respect, please show up on Friday as well. Even if you already presented on Wednesday, you should still come to Fridays. Section or lecture time, so that you can support people that are presenting. Everybody deserves an audience, in my opinion. This is a great stepping stone for you to work on public speaking a little bit, presenting work. You're going to have to do this in research or in a job or anywhere you go, most likely. So it's good practice right now, at least. So yeah, I hope that's clear to everybody. Is there any questions?
Yes. So just a random number of groups will just go on Wednesday and then go on Friday. Is that what I'm getting at?
Yeah, so we're probably going to get 5 groups in on Wednesday, 5 groups on Friday, maybe 6 one of the 2 days. We're not exactly sure. It all depends on how fast everybody goes. So shoot for 10 minutes or 7 minutes of presentation time. That's basically 7 slides. Every slide is roughly about a minute. So don't have 27 slides, don't have 3 slides, have roughly 7 slides, give or maybe plus or minus 1 or 2, but you should definitely shoot for 7 slides or so to fit that 7-minute box. But yeah, 10 minutes, we'll cut it off at 10 minutes per group. Yeah, and more information about this will be posted, exactly what you need to submit on B courses will be summarized in a document or in an announcement. So don't worry about that too much, about the specific details yet. But just know that you do need to show up for your final project presentation. That is required to pass the class, basically. And if there is extenuating circumstances where somebody's severely ill or whatever, please email us. We'll negotiate that or we'll talk about that on an individual basis. But for the most part, everybody should be there. This is very important to us. And then lastly, feel free to apply to be an intern. We're going to send out some information about that. If you want to help run the course, make it better. We have 3 interns right now, Charlie, Pranathi, and Jonah. They've been amazing. They took the course. Yeah, they took the course last semester. They were in your shoes. If you want to join the kind of the staff and help learn how to give lectures, learn how to write assignments, and learn how to do all this stuff and teach and get a chance to teach, you should definitely come. it would be greatly appreciated. Apply, check it out. We love having people to join and kind of keep the class going. Eventually, if you do an internship and you decide that you want to stay, you can also become a facilitator. Both positions are paid currently. Interns get $200 a semester, I believe, and facilitators get $500 a semester. It's not the most money, but hey, we're like one of the only decals in the entire school that pays the staff. So if you want a nice little stipend and like a nice thing to put on your CV, and you want to have fun teaching and all that, you should definitely consider applying to be an intern. And there'll be more information about that either at the end of the lecture or like in an announcement. We'll send that out too. So definitely apply. It'd be fun. We love, and don't feel like, if you don't feel super strong with Python still after this entire course, don't feel like you can't be an intern. Like, we don't necessarily look only for that. We look for somebody who is interested in teaching, interested in helping others, interested in learning more, not necessarily the best coder in the class by any means. So don't feel limited if you don't feel the most confident with coding right now. That's not what we're looking for 100%. So yeah, just keep that in mind. All right. Any last questions about the announcements before I move on? Okay. One little thing I want to add, if you want, support the strike. We are a decal, so like we weren't going to get paid anyway, and we're undergrads, we're not graduate students, so this is kind of adjacent to the whole strike thing. That's why we're still having lecture in the first place. But if you do want to support the graduate students and support fair treatment of your graduate student instructors, the ones that like basically are one of the backbones of the university, you definitely consider checking out this QR code or going to this link and seeing how you can help sign forms, sign petitions, even come out to the strike if you want to picket just for fun. We encourage anybody's like help, I as a GSI and Raphael as a GSI would love any help we can get with the strike and any support. So yeah, if you want to do that, but you don't know how to support us, feel free to check out this link, and that hopefully will answer some of your questions. Or you can come talk to either Raphael and I about it, but don't feel like you have to or anything. It's just if you want to. And then, like I said, I mentioned earlier, we're going to do a class photo. We do this like with every semester. It's like a big thing. I like to show and brag about my students to like my friends and family when I go home in the holidays. I'm like, check out how awesome my students are. Like, blah, blah, blah. They're so cool. This one did this for their final project, and these ones did these for their final project. So I like to brag about y'all to other people and show you to other people in the department and say like, look how cool our class is. You should advertise it in your classes. So we're gonna take a group picture for the whole course, or like everybody in the class on Wednesday. Everybody should be there for their final projects. If you want to pass the class, you need to present your final project and whatnot. So everybody should show up on Wednesday, and we think that'll be the most attendance. And hopefully the strike will be over by then, so there won't be any conflicts about that. But regardless, we're still going to be hosting it in person because we feel that in-person presentations are far more valuable than Zoom ones. So at least that's how we feel right now. We might change that, but I'm pretty certain that's what we're going to do. So please come on Wednesday after the break, and we'll take a picture. Look your best if you want, get yourself all photogenic or whatever. And then we'll take like a big class photo together. I really love doing that, and I think it's a big deal. And I also have rewards for everybody who finishes their presentation. I have stickers, so you should definitely come. Cool. So I think that's everything on announcement side. Yeah. So today's lecture is going to be a little bit on machine learning. Just I wanted to touch on it briefly. I think it's a really cool concept, and I want to we're not going to do nitty gritty details. I'm not going to show you lots of lines of code, but I just want to give you kind of an overview of what machine learning is. Python is usually the language of choice for people to go into machine learning. If you want to learn some really cool stuff, we'll point you to some resources to teach yourself a little bit about machine learning, or classes you can take if you want to learn about it. But I think it's like one of the coolest things. It's kind of tangential to everything we learned, but it still reuses all these concepts that we talk about in Python. And it's just such a cool field that's literally booming right now as we speak. It's being developed as we speak. Every day there's a new paper, or there's hundreds of new papers coming out on new techniques and new ideas that come up with machine learning. The ideas came up like 50 years ago, but they weren't practical until now. And so this is a booming field, and textbooks are being written every week, it seems like, with updated information and new information. So it's a really, really cool thing to get into if you're interested. And then we'll talk about some concluding remarks for the course, and Megan will take over for that. But we're going to do half the lecture basically on machine learning. So what is machine learning? Well, it's kind of teaching the computer how to do stuff. And there's various reasons why we do that. So programming in real life applications is really hard. So if you're trying to come up with an app for, that takes into account like I don't know, like all the nitty gritty details of nature. Nature is just imperfect. There's lots of variables that are at play that we don't even know. Maybe you're like writing an app that tracks driving or something like that. Like the road, like roads, air, rain, snow, all these things. You can't like code every little detail. What happens if a person gets in front of you? What if the stop sign is bent instead of perfectly the way it should be? Everything in reality is a lot more like, it's just not perfect. It's like too many factors to code. There's so many details to think about. So real life applications are really hard to program for. But what if we instead said, okay, we don't really care about all these if statements and these clauses and like what to do if this is not perfect or if this is not perfect, and try to anticipate every little thing coming up. But what if we just taught the computer how to learn through examples? Kind of like how when an infant learns how to speak, they don't learn because like infants don't learn by opening up a book and reading the grammar of the language. They listen to their parents, they listen to friends, or like the parent friends, the family members, they listen to all the sources around them, the TV on or the radio, all of that is being processed, and they're trying to figure out what all of it means. And then eventually they mimic it. And eventually they like learn all the nitty gritty details when they get old enough to learn it. But that's how like we first learn how to speak in the first place, or listen. Start to learn what things mean. We learn by examples because there's just so much information. Every single person has a slightly different tonality to their voice and accent, maybe. So exposing our ears to lots of examples really early on allows us to kind of create a model of what language is, and then we start using it, and then it gets corrected and refined and so on. So you can kind of think of a computer as the computer has the potential to be like an infant child, but way less intelligent, basically. And we're teaching it specific specific like tasks, not necessarily everything, like all of consciousness, that's a long ways away, but at least like how to do a specific task. We can teach it like baby steps and stuff like that. So that's what we're going to talk about today. So machine learning applications, this is a lot more places than you think, and it's still growing every day. There's more and more applications being found and refined and learned how to do. So for example, self-driving cars, you've probably heard about this one with like Teslas and whatnot, and other cars that are coming on market. Netflix and TikTok recommendations and Instagram recommendations, all of this is through machine learning algorithms that monitor, that take in all the data of the users on like huge scales, and then they make predictions about what you're doing or like what you would be interested in. Same thing with advertising. Siri and Alexa speech recognition, and anytime you ever use any of those are definitely using machine learning to process like your tonality, your voice, and try to interpret what you're saying. Google Translate is another one. It uses machine learning. Medical diagnosis, and then like face recognition, all software, all of that stuff. And then there's even more. I didn't even come close to all of it. I just talked about a few examples here, but it's everywhere. Literally everywhere. And it's only getting bigger now. So machine learning is a very practical and useful application of programming and like the capabilities of what we could do with a computer. It's pretty cool. So any questions on what I've said so far? Okay, we'll keep going. So there's usually two types of machine learning in a broad sense. There's supervised learning and unsupervised learning. Well, supervised learning means we develop a predictive model based on both input and output data. So what do I mean by that? I mean, I have data that I feed into it, and I also I have inputs, but I also tell it what the specific outputs of that data, of that like model should be. So if I put in, I don't know, like a picture of like an object, but it's a cat. Like I put in a picture of a cat. Supervised learning would be like, okay, I tell the computer, this is a cat, and here's the picture. Try to learn why this is associated with this. And I give it lots of examples, and then it tries to come up with a model of a cat. Same thing with like the word dog or like a keyword. You give it labels. We call them labels to data. So unsupervised learning is when you don't give it a label at all. You just give it data and it tries to find patterns inside that data on its own. So supervised learning is usually used for classification, classifying images of cats, of dogs, maybe classifying handwriting into numbers, classifying or like looking for, I don't know, maybe like plagiarism, stuff like that. Regression, for example, is another form of supervised learning. That's basically like fitting models to data. We've already touched one form of regression earlier in this course, and I'll talk more about that later. But just think of it basically like fitting models to data. That's basically regression. And then unsupervised learning would be like clustering. So that would be like coming up with like trends or patterns, like how is the data clustered? But I don't know what those clusters would be beforehand. I'm looking to the computer. I'm asking the computer to find the most like the closest like I guess groups. Like what are these groups that the data can fall into? Like how do I classify it or cluster it? So that's unsupervised learning. And unsupervised learning is a bit more complicated, but we'll talk about that in a bit. So in summary, supervised learning is where you give input data and labels of that data. So you tell the computer, this is what that data is. This is what it is. This is what I interpret it as. And then it will output more predicted labels. So you feed it a bunch of training data. It learns all, like the model will learn all of this stuff. It'll like learn why, like correlations, like that. It'll try to figure out correlations between this image of a cat and the word cat. It basically tries to associate these two and look for patterns that like multiple patterns. And the only way this is possible is if you feed it tons of examples. So tons of different looking cats, tons of different looking angles of the cats, all that stuff. But if every one of them is called a cat, it can create kind of an image or a model, like idea of what a cat is. Same thing with like a dog or whatever you want. And then so like the two most used like two most common uses of supervised learning would be regression and classification. Like I said, like regression, you can think of it as like fitting to data. We talked about basic linear regression already. That was when we used scipy.curvefit, least squares regression, like least squares fitting. That was a form of regression, just linear regression, basically. We use that to fit, sines and cosines to like periodic data, to fit quadratic formulas. All of that was using a form of machine learning. So you've technically already done machine learning in this course, which is kind of cool. And then classification is like, is this image a person or a car, for example? That's like classifying stuff. And we'll talk more about that in a bit. And then unsupervised learning would be you give it no labels, but you still give the input data, but you give it no labels and it tries to figure things out. So a common example of this might be Netflix giving you really interesting like classifications or like genres of movies. If you've ever gone on Netflix and just binging down and you look for like different movie genres, you might find something like violent thrillers about cats for ages 8 to 10, or like chilling goofy movies. I don't even know what this is down here, but I don't want to know. Like, so these are like not made by a specific person. There's not some crazy psychopath at Netflix that looks for, like, comes up with all these weird, obscure, like genres and watches every movie and puts them together. It's a machine learning algorithm that's just coming up for looking for similarities between different films, which is a pretty cool concept. Is there any questions?
Yeah. So, I just want to have some questions about like examples of machine learning, like or examples like those websites where you would type in a word and then it would output a piece of art. Does that count as machine learning? Like, have you seen like those?
Yeah, that's a great question. And we're actually going to do that in today's lecture. So hang tight on that. But I'll talk about exactly like what that is doing, but that is a form of machine learning. Exactly. Good job.
Okay.
Awesome. Okay, so let's keep going. So talking about regression a little bit more specifically, it's like there's many different types of models you can use: linear, polynomial, logistic models, whatever you want. We're not going to talk about all the nitty-gritty details here, but basically you calculate the parameters that minimize the loss given input data and output labels, aka an X and a Y. Now you might be thinking, well, what is loss? Well, loss could be, it's loosely defined. You can define it however you want. There are lots of different common loss functions. For example, one might be the residuals, aka like the distances between the points and the line, or like the curve you're fitting. That's one really common form of loss, and that's what least squares linear regression does. That is a form of, you're calculating the loss and you're minimizing that loss between your model and the data. But there are other more advanced like loss models that you can like functions that you can use, but that's usually the easiest one to understand. And the real data is never perfect, so there's always going to be some sort of errors or noise. And it's important to consider simplicity versus overfitting. So on the bottom here, we show an image of underfitting, balanced fitting, and overfitting. There's a clear trend here, but there's a lot of noise in the middle. So the middle would be like a good example of like a proper fitting. But if you overfit, you give the model too many parameters, it'll try to make this like crazy, it'll go through every point where that's not really the model we're looking for. And if you don't give it enough parameters, it won't be able to figure out the trends. So there's a whole bunch of science to this, and this, if you want to learn the details of regression and all this, you can take more classes on this, but there are lots of different like techniques that we can use to like make sure that our fits are robust. They're not overfitting, they're not underfitting, they're doing it just right. So that's basically regression in a nutshell. And then using data, you could split the data. Like typically when we do machine learning, you always split the data into a training set and a test set. So the training set is to train your model. So you give it a bunch of data with labels or no labels, depending on what kind of learning you're doing. But you give it a bunch of data to test on or to train on. And then once you train the model on this data, you use it on the, like you use that model on a test set of data. So the testing the test set of data is to evaluate the accuracy of your model before using it on never seen data. So if you give it all the data you have to train on, it'll be really good at working with only that data, but you don't know necessarily how it will do when you give it new data that's never seen before. So the reason why we use the training and the test set is to train it like on like just some data, but then see whether or not it works well on a test set. The most important thing is to have a high test accuracy as opposed to a high training accuracy. A high training accuracy means it's very nichely fit, like this overfitting example here. It would look like, it would be kind of like this, where we want something more like the middle. So yeah, don't use your test sets as your training data. That is a big no. You want independent evaluation. So for example, this is like a good example of like using machine learning, like with data on classification. So this is a supervised form of learning. Like given many data points with different class labels, you are then asked to predict or classify new data points. Maybe or for example, we have to define like a decision boundary to split the data up. And often the data is not really easily separable, or it's like kind of like mixed and mashed. So it's hard to really describe exactly what that boundary is. But we need to balance like the test training or the training accuracy with the test accuracy. So for example, on this left image here, we have two types of data points, yellows and blues. And this is where you have an extremely high training accuracy, meaning you give it the input data, or we give it all like really good training data. You give it lots of parameters, and it can really make these like crazy border lines where it's like splitting every single like yellow from the blue, but that doesn't really get the overall picture. If we apply it to a test set, we would get something completely wrong. But if we balance that a little bit more with like balance the parameters that are disposable that we can use, and like go more for like a balanced fitting as opposed to an overfitting, then you'll see when you apply it to the test set, yeah, there's some blues that overlap in the yellow region and there's some yellows that overlap the blue region, but mostly the general trend here is what we're looking for. Roughly, how are these classified? Where do the yellows fall? Where do the blues fall overall? So this is a good example of classification with machine learning. Again, real data is noisy. It's not perfect. So you're not like, unless you want like an absolutely perfect like example or like use case, then you're mainly going to want like the broad overall ideas here. You're trying to get the gist of what's going on. Just like when you're learning a language when you're young or like an infant, you don't mimic every single person's speech, tonality, and dialogue, or dialogue and accent. you create your own, but you get the gist of what the language is doing. That's kind of the same thing here. So we're getting the gist of the classification scheme here with machine learning, and that's what computers are pretty good at. So is there any questions before I move on to a demo of this? Okay, so normally I would run this live, but since I'm on Zoom and we're recording, I have a feeling it would like lag a lot. So I recorded it beforehand. Fear not. Yeah, so if we look here, this is like an example of like using this code. So, or using some code. So really quickly before it runs, I have like a demo here made called facedetect.py. It's just a Python file using a library called OpenCV, which is really good for, it has like pre-made like machine learning models that classify faces. So you can like hook it up to your camera on your, like on the laptop, which is what I did, so that it takes in live video like of me or like my Zoom camera. And it can detect faces within like the video, so in real time. So if we run the script, we see a window pop up and there's my face and it's working. You could see a green box around my face, and it also works for other faces like Raphael's. He looks very confused in this image, but it found his face and it found my face. And if we were here in person, I would flip it around and it would catch all of your faces in the audience. And this is one example of a Python library that is very useful. And you can imagine it has a lot of surveillance applications, and it's really creepy and it freaks Raphael out. But nonetheless, it is like a really cool thing that you could do. If you're interested, Google OpenCV Python. You could pip install the package right here, pip install OpenCV-Python. You can clone the repo from my GitHub if you want and play with it yourself. So that's one really cool example of machine learning. I would run it live, but it's like Zoom makes it a little bit laggy. Anyway, so is there any questions on that? Okay. I just want to be clear though, that package I used has pre-trained models. So they took tons of images of faces, like thousands or hundreds of thousands or millions of images of faces, and had their machine learning model learn on the training set. Their training set was all the data they had over there, or most of the data they had over there, and they trained it on images of faces to track what a face looks like. And then once they made a model that was robust enough for test data, they then put it into a Python package and shipped it off. And now we can use it for our own, detecting our faces and whatnot, which is pretty cool. Where am I at on time? All right, cool. I'm running a little behind, so I'll try to speed up a little bit. Another really interesting form of machine learning is through neural networks. Or like this is kind of like the backbone of like a lot of machine learning like models, like how they are formed. We use neural networks, which is taking a page out of biology's book. We know that the brain works by having neurons that have like basically like a, I don't know, like what is it, like the dendrite or like a synapse. They have like the nerve bit and they have like the node at the end. I don't really remember the biology words here, but you could kind of mimic that on a computer where you have basically layers of functions or nonlinear functions and linear functions to model any function. You're basically superimposing all of them. So the combined effort of lots of little functions working together, like correlate, like in tandem with each other, basically mimics like neurons in the brain, which is a kind of a cool concept. And when you have lots of layers with lots of different nodes, then you can basically train the model, like the model can like come up with like a learned idea of what is going on. It's very like black boxy. So if you like put it in a black box in the middle, it basically what we get is given a bunch of input parameters that might seem uncorrelated or whatever, you get like an output of like either a yes or no or a classification of something. For example, if I want to determine whether or not this person is happy, I don't know, whatever that means, but like maybe like if you want to learn, like wanted to determine whether or not it's happy, you give it all these parameters and then the model will learn based off of your like your label of either yes or no, yes, this person's happy, or no, this person's not happy. It'll take all this input data like inside this neural network, and then it'll give you a yes or no decision once it's trained on enough data. this has been used like on like a social media study. People were able to accurately predict like with like 80 or 90% accuracy, like a person's like marital status, their socioeconomic status, their education, or like their education status, and like a whole bunch of like 20 different really creepy factors just from the likes and the comments on their Instagram posts. Like you can use neural networks to do stuff like that. Very, very crazy stuff you could do with neural networks. And all the weight, like all these intermediate weights inside of this, like in this neural network, like all these like little like lines, connecting lines, have no real physical meaning. At least we don't have an explanation for what it is, or like what it means, but we know that the end result kind of works. So it's like kind of a gray area in science to use it. It's like, is it like actually like, can we, like, how could you use this for science if it's not necessarily like reproducible or like not like factual? It's like we don't even know what's going on in the middle. It's like a very interesting idea, but it can be used for some pretty crazy stuff, and it does work, and that's why we use it. So it's basically like giving the computer like a mini brain for like simple tasks, I guess you will, or at least like reasonable tasks that are not like, you know, we're nowhere near general intelligence. So don't be freaked out if you think like, oh no, the computer, like a neural network will end all of humanity and all this stuff, and the computers are going to learn everything about us. But it can get really good at like specific tasks, which is interesting. Yeah. Oh, yeah. So we just did the face detection demo with that was using that, like whole model was created using a neural network. That's kind of like the backbone for how models are trained. And some examples of machine learning in astronomy might be, okay, let's give a neural network tons of input images of what supernovae look like before and after. Let's train it on like, here's a before and here's an after image where we see like basically a really big bright spot where there was a dim spot. And we train a model with the neural networks. We'll give it thousands and thousands of images of what this should look like. And then eventually the computer can get as good as the human eye at detecting whether or not something is likely to be a supernova or not. So this is a very common thing. This is used in the Zwicky Transient Facility down, what is that, by Caltech, I think? Yeah, by Caltech. So like, that's like a really cool thing that's discovering thousands and thousands of supernovae like every week or every month or something crazy like that. I don't even know what the numbers are. Something that was like never possible before machine learning. So now we're finding tons of data and learning lots about like explosion mechanisms of stars and stuff. Similarly, you can use it to classify galaxy types. So there's lots of different kinds of galaxies, but the main like kind of categories is like ellipticals, unbarred spirals, lenticular galaxies, and then barred spiral galaxies. So you can train a model with lots of images and labels to classify different kinds of galaxies, which is pretty cool. In fact, there was a really cool competition on Kaggle, which is like a data science like competition website that hosts lots of data sets and competitions for money. And somebody like, this was like one of the prizes, or like one of the like prompts or like questions was like build a model to be able, or like a neural network model to be able to classify galaxies. And it was like a really cool thing. I think they got like 97 or 95% accuracy or something like that on the test set. So that was really cool. This is just a couple examples of machine learning in astronomy. And if you're interested in like learning about this stuff, feel free to check out some really cool Python packages. TensorFlow, Keras, and PyTorch are like the kind of the three go-to packages. PyTorch is more used in a research setting. TensorFlow is like built by Google, so it's more industry oriented. And then Keras is kind of like a higher level. You don't really need to know the nitty-gritty details of everything, but you can use it more on a higher level. They have tons of tutorials. We're not here to teach you all these little details. This isn't a machine learning course. But if you want to learn, you're more than welcome to come go check those out. I think they're really valuable and really interesting and really well written. They have, you know, millions and millions of dollars of funding. So they have really well made documentation that's very explicit and very clear. If you want to take an actual course on it, typically, I don't think Data 8 really covers much machine learning. But some other really useful courses like Data 8 for Intro to Data Science, Data 100 is advanced data science techniques. But then if you want to learn more about machine learning, you could take CS 188, which is artificial intelligence, and CS 189, machine learning. Granted, this one is very theoretical. It's very like, if you want to learn like the mechanism behind the black box that is a neural network, you can learn about all of that in CS 189 in great detail. And we put some links to classes that you can take a look at if you're interested. Any questions on any of that? Okay. If not, then we'll keep going. I have
a question.
Oh yeah, go ahead.
So which class will give you a better hands-on experience of coding, like with machine learning?
I think the best class, if you want to just like play around with it, not necessarily learn all the like underlying principles of it, would probably be like Physics 188. And we'll talk about that like at the end of the class a little bit. That's like a physics machine learning course that talks about Bayesian analysis as well as machine learning, and you get to do some really cool stuff about it. And I'm going to talk about one of those things you can do with it. So we're going to talk about generative models. This is like a really cool thing. I'll try to keep this quick because I think Megan has a bunch of stuff she has to talk about. So really quickly, generative models are really cool, like application of machine learning. They're very new, like it's a very new concept within this past 5-10 years, I think, or less, honestly. You can like basically teach a computer how to label the data, which is what we were talking about. That's like everything we've been doing, how to classify data. But if you are careful with the way you do this, careful in the way you train it, you can actually generate what it learns from that data, or like from that, like it learns like what this, like what something is, and then it can generate that itself. So for example, let's say I show lots of images of fives, of like the number 5, like hand-drawn pictures of like thousands of hand-drawn pictures of fives. The model can actually, if you're careful with the way you make the model, you can actually have the model learn how to draw a 5 itself. Not necessarily say whether or not an image is a 5, but draw it itself. And we call this a generative model because it literally generates new data from its learned model. So the details of this are really confusing. If you want more details on that, like this is like the final project of Physics 188. It's really cool. And this is like kind of an example of what I'm talking about. So you feed it tons of images of handwritten numbers. Call this the MNIST dataset, M-N-I-S-T. It's one of the biggest like standard datasets ever used in machine learning, with just handwritten digits. Each digit picture has a corresponding label to it. And then basically we feed all of this into our model. And the model, if you give it enough like iterations of like learning, like enough practice learning with the data, it gets better and better at drawing different digits. For example, this left column is what it thinks a 4 looks like. This second column is what it thinks a 2 looks like. This third column is what it thinks a 0 looks like, and so on. Granted, these are only 100 iterations. It gets better and better with like thousands, but it takes a long time for the computer to, it needs lots and lots of data to be able to draw basically its own, or generate its own version of numbers. So, but it's a really cool idea. And this can be used in lots of different applications. For example, if we feed a neural network or like a model that can be generative, like simulations of fluids, for example, like water sloshing around, like droplets hitting water in a bucket, we can actually train a model to learn the laws of physics for fluid dynamics, and then it can generate its own simulations from that. Oh, and you could get like stunning accuracy. It's kind of insane. So this was made, this was not real. This was made, this right image is made entire, video is made entirely from a neural network that learned the laws of physics on the left side. This is a really cool thing in research. I think like maybe 5-10 papers have come out in the past, like, you know, few years on this stuff. It's very, very new. It's very, very cool. And it's like bleeding edge applications of machine learning. It's very cool. And with that, I want to show you a really cool example. So these generative models is where machine learning really, like, I feel like has some fun applications. And some of you might have heard about Dolly. This is a
Yes, I have.
Yeah, it's an AI system, a generative neural network model that they feed it tons of images from the internet. Basically, they give it every image on the internet they could find with that's like not inhumane, and give it like labels that are like all, as long as it's labeled. So like, this is an image of a cat, this is an image of a dog, this is an image of a person, this is an image of a school, blah, 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 blah. And then it basically learns how to generate images from that. And I have I have access to it right here. So if anybody wants to, please feel free to type in a chat. Give me one prompt at least, like anything. It could be literally anything. So just for an example, maybe I could talk about a bear riding a skateboard on the highway while being chased by police. And I'll make it in this digital art. I want to see it like in a digital art format. And we'll generate this. And so it takes some time. It's the model's training, or the model is like generating. It's like trying to figure out how to generate an image from this. And these are some examples of what it generates. These are never before seen. You are the first people to ever see this image ever. These are not like made by an artist. This is made entirely by a computer, generated on the fly. So for example, any one of these are like examples where it's a bear riding a skateboard on the highway while being chased by the police. And the more specific you are, the better it is at what it's trying to do. I can't.
Insane.
Yeah, it's really cool.
Oh my God.
Yeah. So for example, here's another one that I found, or that I did. Here is I typed in photograph of a golden retriever with sunglasses riding a skateboard. Those are not real images. Those are entirely generated by a computer, which is really cool. Yeah, I'm trying to access the chat, but it won't let me for some reason. Give me one sec. Let me try to access. Oh, here we go. I got it.
Oh, okay.
Is there anybody? Go ahead and give it a go. Well, I'll try one person from the chat. Just anything random. Give it more detail. I need lots of detail. Yeah. Anybody, feel free to type anything in the chat. It could literally be whatever. For example, what? That might be a little specific. We'll see though. We could try. I'll try to make it. So Oski Bear defeating Stanford University in a football game on the grass field. And then we'll do it in the style of Van Gogh.
Add an axe to the description.
Okay, and with an axe, defeating a football game on the grass field with an axe in the
I was
style.
gonna say the Stanford tree with an axe.
Okay, gotcha. The Stanford defeating University
Hitting?
tree
Yes.
game on the grass field. Let's just see what it does. It might be like, what? That was
We are giving it new data points. Oh, never mind.
yeah.
That's
So,
amazing.
yeah, that's just one example.
Wow.
We could do more of this after lecture, but Megan needs to give some final remarks on the course. But this is just one example of how machine learning can be used to generate new stuff from what it learned. So the input of this was just tons of images with labels, and this company, OpenAI, created a tool to be able to do this. And they also have a tool that generates code. So you can tell it like, make a video game that does this, this, and this, and this. And it can literally write code to do that. Like it,
Wait.
yeah, no, it's crazy. It's called.
Where?
For example, if you're curious, it's called OpenAI Codex. I think I have access to this too, but I haven't dug into it. And if you want you tell it what you want it to do, and it'll write code for you in whatever language you want, Python, JavaScript, whatever. And you can make games on the fly, for example, or pull data sets and analyze them and plot them just with telling it what to do. So now I think Megan's going to take over the lecture and give some final remarks on the course. Hopefully it's enough time. Sorry, Megan.
I think it should be fine.
All right, cool. I'm going to stop sharing.
Oh, okay. Me. Oh. Okay. So congrats to everyone. You guys basically finished the course. I mean, there's like still 2 weeks left. You guys have to do your final projects, but this is the last lecture. So you guys are pretty much finished. So great job. Round of applause. That was just me. Anyways. So you guys have learned a lot in this course. So you've learned all the basic Python skills from data types to object-oriented programming. You learned how to use external libraries, NumPy, SciPy, Pandas, all of that. And today you guys learned machine learning. You guys also know to make really nice plots. With the ultimate plotting guide, you guys will probably use it in the future. I know I use it. You guys can make and use simulations from using the differentiation integration in the animation lecture. And we also taught you guys some professional development. So we've shown you how to get research. We've showed you guys how to write your own CVs and make your own websites, some LaTeX and GitHub. So you guys have learned a lot in this course. I know it feels like it went by really fast. Like I felt like the semester went by really fast, but I know in like future recording courses, like they'll be so much easier now after you've taken this course. Like for me, when I took this course, after that I took 61A and I thought it was like pretty easy after taking this course. So yeah. So what's next? You have a lot of like more opportunities to keep coding in Python or learn more about coding. So you can apply to research. We taught you guys how to do this in the last lecture, and that lecture and this lecture should be uploaded by today. If it's not, and you guys want to see it like right away, like let me know, because it just takes like forever to convert. But basically, like you can cold email, you can like go on websites. I know the Astro department has some links to resources for coding, not coding, for research, but at least in astrophysics, a lot of research is coding. So after this course, like this is pretty useful. And you also have your final project to put on your resume and be like, hey, I did this. I know Python. Even if you think that you're not like that well versed, like just getting more experience with coding will help you a lot in learning Python and keep growing as a coder. If you want to learn more skills, you can take physics 77 or 88. A lot of our homework questions are based off the questions that that course uses. So it'll be pretty easy for you guys, I hope. There's also data 8 and data 100. Data 8 is, I would say, more similar to like the NumPy portion of this course and all the data manipulation. Data 100 teaches you some machine learning. Physics 188 that James briefly mentioned, you learn iterative Bayesian analysis and a lot of machine learning. I think that's more focused in the physical sciences. So if you're astro or physics or in that area, like this course, and you're interested in machine learning, like this course is really helpful. Astro 128 is a data lab. I've seen like, I think James, he would like have all these like Python, like Jupyter notebooks, and they're like so much coding for the course, I would say. So if you're like in between like one of the labs and you're not sure which one to take, but you really like coding, I would take the data lab. Also, if you like want to delve into the CS realm, you can take 61A. It's a lot more rigorous than this course, but I found it really useful. And it helped me a lot in my coding skills. It's not as hard once you've taken this DeCal, in my opinion, but to each their own. And lastly, if you want to help teach the DeCal in the future, we're going to send out a form after the final projects, and depending on how many people apply, we might have some interviews, but they're like really low stakes, and it's like really chill to get in, like don't worry. But yeah, if you're excited and you're passionate about this course, we'd be happy to have you. Course evals, intern applications, I'll send all these links in an announcement once final projects are over. The course eval form is basically the one that we shared before, but now it's the end of the semester and we'd like to hear feedback, whether it's something you like or something you think we can improve on. So thank you guys for coming. Good luck on your final projects and we'll see you guys in 2 weeks. Have a nice Thanksgiving.
Yeah. Woohoo. And I just want to say this is my last time teaching the decal. So y'all are my last hurrah. So good job. And yeah, thank you everybody.
We should give James a round of applause.
It'd be cool.
Bye, everyone.
Thank you. Have a good weekend.